Hello everyone, welcome to Multivariate Statistics in Machine Learning. In this video I will be discussing limits of correlation, especially when you have nonlinear relationships. If you'd like to study this yourself, then look into the lecture notes in the section 6.1. Okay, so what is the problem here? So often in reality, so when we use correlation, so correlation implies linearity and the other way around. So if you remember, we have like a simple regression setup. We have some regression curve, and if it's a linear model, then it will look like this, so linear regression. And then we have some data scattered around this curve here, and if it's not too far off, then it will be a nice and strong relationship. And this relationship is described by the correlation between x and y. And if this is univariate and that is univariate, often you can also look at the squared correlation, and then you have a measure of fit of, that's a number between 0 and 1, and then we basically can see how well the regression line fits this curve. So now what happens if we have something like this? So let's say we have a parabola. So again, this is x and this is y, and of course locally it looks like a linear relationship, but overall it's of course not. It's a non-linear relationship, so non-linear. And the question is, if we compute the correlation, and that's what you will be doing or end up doing when you're a data scientist, you will be computing a lot of correlations. So the truth is that we have a nonlinear relationship, and what does the correlation tell us? What's the correlation? So to do this, let's do a little experiment. So we go to open a computer program. So I open RStudio. Here it is. And then we do a little simulation. So let me shrink the window a little bit so you can see me. So here we go. So that's the R session. And now let's just simulate some data. So let me type. So let's simulate 10,000 normal distributed random variables. So x is R norm, let's say 10,000, right? So that's our random numbers. And now we transform these numbers. So we compute the square of the x to give our parabola. So we have a quadratic relationship, and that's 100% perfectly well-known relationship. So what happens if we compute the correlation between x and y? And surprise, surprise, it turns out that the correlation between two perfectly deterministically connected variables is actually 0. So let's go back to our little pad here. So the result is if this is just if x comes from n01, and y is just x squared, then the correlation between x and y is approximately 0. So that's of course not a good idea if you would like to find out whether these two variables have actually a relationship. So it could be any biological process or some engineering process, and we thought that it might be a good idea to figure out, are these things correlated? Are they potentially in a causal relationship? I mean, if you study causality or models for causality, you will always see that the correlation is the shadow of causality. So if there is some causality, then there is some correlation, but from correlation you can't infer directly to causality, of course. But if there is causality, there must be some correlation, if it's a linear relationship. So the conclusion of all of this is that if there are nonlinear relations, then correlation doesn't help us to find these dependencies. So nonlinear relationships in the data then simple correlation is not able to detect the dependency. So we've seen in the previous video, when we talked about measuring dependence between vectors, we discussed the Roseboom vector correlation, and I showed you how to derive it using mutual information. So mutual information would be capable here, perfectly capable to indicate whether these two random variables are correlated, in quotation marks, I mean dependent or associated or not. So that's one thing. So one thing is, you need to keep in mind, whenever you measure correlation, you will only find the linear dependencies. So now I'd like to show you something else that's related to it. That's the very famous quartet of data sets that look completely different, but they have the same linear characteristics. And this data set is called the Anscombe data set. So let me clear this here. So conclusion, just write down the conclusion again. Conclusion. From correlations, you cannot infer about nonlinear relationships. So you need to do something else, and this something else is often mutual information, but there are other ways as well. And of course the other alternative will be to use nonlinear models. And that's of course the theme of the coming 2 weeks in this course. So that's the motivation. So but now let's look at the famous Anscombe data sets, and I'll show you the paper now. So let me open the PDF. So it's from 1973, this paper. So here you can see it, and it's called Graphs and Statistical Analysis. And it has become really famous because it clearly demonstrates that if you just look superficially at the data, you may miss a lot of things. So, and he's arguing in this paper for visual interpretation. So that's really very, very important. So you should always do visual inspection of the data if you can. So that's part of exploratory data analysis. So this is the data. So these days you actually didn't have GitHub or something. You would put the data straight into the paper, and so you have various responses, and it's the same X variable. And the whole point about this is that we have a couple of data sets, and they all have the same means, the same regression coefficients, the same sum of squares, regression R squared, and so on. And if you plot those, you can see that they are extremely different. So this one is, so in this first graph here, that's what you would expect when you have linear relationships. So you have your curve here, your fitted linear model, then you have some data, and then you have a regression coefficient. In this case, B1 is 0.5, and then you have a mean of the X, mean of the Y, and so on, and they're all the same. And because all the first and second moments are the same, of course, all the linear measures based on first and second moments are the same. So now, so that's fine. So the first plot, figure 1, is okay. Figure 2, it starts where it becomes really concerning. So clearly we have a non-linear relationship here. So that's kind of the case that I showed you in the simulations. So we have some sort of a maybe quadratic curve here, and yet if you haven't looked at the data, this has exactly the same fitted regression curve, the same R squared, the same everything. So it's, in terms of first and second moments, it's indistinguishable from this. So, but it goes even further. So he has two further examples. So this one is an example where you have an outlier. This shows you the effect of an outlier. So clearly the regression curve is wrong. So the regression should be, if you're into the linear relationship, so there is clearly a linear relationship with an outlier, and what you have to apply here is either a robust method that actually automatically detects the outlier, or you have to inspect it visually and then remove it by hand. And that's, of course, a crucial step when you do practical data analysis, that you actually have to clean the data and you have to detect outliers. And obviously, sometimes the outliers are the important bit. So both the outliers are important, and of course the main points are important, but there are different things and they need to be analyzed differently. And of course, an outlier is always defined relative to the main group. So this is one example. So these also have the same linear things, and the same thing is true here. So where we actually have, we don't really have a linear relationship, and still, because there's also an outlier here, the whole thing altogether has the same characteristics of this one. So these four datasets are the famous Anscombe datasets, and they are of course now a little bit dated, but they still show the key things. But there's a fun dataset that you will be analyzing in the worksheets, that where somebody actually wrote a program where you can basically move your data points into almost any shape, and they can take on some funny forms. So if you look at it, you see clearly that there's nothing linear in this dataset, but yet they still have the same linear characteristics. So that's the conclusion. Basically, you can have completely different data with identical first second moment, and first and second moments are the linear, so they have this share the same linear characteristics. So they all have the same correlation. So this is another illustration that looking just at correlations can be misleading. They're often useful, but they can also be misleading. So that's for this video today. In the coming videos we'll be using, of course, now focusing on nonlinear, non-pragmatic methods for both for classification and for regression. Okay, so bye bye and see you next time.